Greetings, students. Here we are again, thinking about logic. And today we want to think about something called natural deduction. Natural deduction was first developed by the logician and mathematician Gerhard Gentzen. He began to get frustrated with the way proofs were done, proofs in logic, and he had this thought. Ich wollte nun zunächst einmal ein Formalismus aufstellen, der dem wirklichen Schließen möglichst näher kommt. So ergab sich ein Kalkül des natürlichen Schließens. Or, first I wish to construct a formalism that comes as close as possible to actual reasoning. Thus arose a calculus of natural deduction. Now, I myself have found it to be a little bit closer to how I actually think, but more importantly than that, I've found it to be a lot of fun. It's almost like a game, which I hope to introduce you to. And it's much more fun than mechanically calculating out like we've learned to do with the truth table. So let's begin to think about that. Suppose you know the following facts about Dr. Getch are true. Dr. Getch can join the Red-Headed League if and only if he has red hair and is of Irish descent. Dr. G can't join the Red-Headed League, and Dr. G has red hair. Can we use these facts to prove that Dr. G is not of Irish descent? Now, Sherlock Holmes might reason as follows. My dear Watson, if it's true that Dr. G can join the Red-Headed League if and only if he has red hair and is of Irish descent, then it's also true that if Dr. G can join the Red-Headed League, then both he has red hair and is of Irish descent, and that if he both has red hair and is of Irish descent, then he can join the Red-Headed League. But if that is true, my dear Watson, then it is also true that if he is both red-headed and of Irish descent, then he can join the Red-Headed League. And if we know it is true that if he is both red-headed and of Irish descent, then he can join the Red-Headed League, and it is false that Dr. G can join the Red-Headed League, then it must be true that it is false that he is both red-headed and of Irish descent. And if it's true that it is false that he is both red-headed and of Irish descent, then it is also true that either he is not red-headed or he is not of Irish descent. And if it is false that he does not have red hair, and either he does not have red hair or is not of Irish descent, then we may conclude with certainty, my dear Watson, that Dr. G is not of Irish descent. Well, that's one natural way to reason, but there's sort of a way to streamline this and make it easier to deal with. And this is what we're going to learn how to do, right? First, we would translate the argument in the way that we've learned, right? J, if and only if, R and I, not J, R, therefore not I. And then we begin to apply rules of inference and can essentially put it in a form of a calculus that's much easier to deal with than the English language version. Or at least I hope you'll find it to be so. And kind of fun too, as you'll see. Lewis Carroll called this the game of symbolic logic. Now, we've learned the method of truth tables to establish validity. But as you may have noticed, truth tables can get quite complicated the more premises we have. 2 to the nth power, remember. So if you have 5 or 6 separate propositions, it begins to get rather unwieldy, even if we use the method of truth assignment. Now, truth tables give us what is called a semantic proof of validity. They graphically display that it's impossible for all the premises to be true and the conclusion false. But the method we'll use now is very different. It's sometimes called the method of proofs, or as I've said, the method of natural deduction, as Herr Gentzen called it. Now, this is related to truth tables, right? Because we use truth tables to validate the rules we use doing proofs, which is a very valuable independent confirmation of the concepts evolved. And you learn this through doing your homework, in which I had you do a truth table for each of our 8 inference proofs, which I've been introducing you to all semester long anyway. So they ought to really be up in your head. Okay? Now, no one but a computer uses truth tables in its everyday workings. But the method of proof seems more intuitive. and has been around since the Greeks first codified logic and geometry. And you may be familiar with the method of proofs from doing geometry and the method of Euclid. Though if my daughter's example in high school is any example, the teacher probably blew through it too quickly to do you any good. Right? Natural deduction builds on that kind of thing we find in Euclid and includes the symbols that we've learned in symbolic logic. And natural deduction then can sort of show us exactly step by step how a conclusion can be derived from the premises. Proofs in logic, like proofs in geometry, move in a series of little steps, one after another, each depending logically on each other. And each step is like a small argument in a chain of arguments, which demonstrates the logical links in a chain that necessarily leads to the desired conclusion. And if you can get from the premises to the conclusion by valid steps, then the argument as a whole is guaranteed to be valid as well. Now, proofs can sometimes be difficult because you have to see the links between the steps. It's not mechanical like the truth tables. There's no algorithm or mechanical decision procedure. If you haven't found a proof, it doesn't mean that the argument's invalid. But if an argument is valid, the proof will show the connections between premises and conclusion far more clearly than any truth table ever could. In doing proofs, we move from one step to another by using what are called valid inference rules, or rules of inference. Any inference which has these forms or patterns can then be used in constructing a proof. Initially, we'll learn to use 8 inference rules, and then we'll add 10 equivalence rules, which are a little different. But first, I mentioned Lewis Carroll before in his game of symbolic logic. Let's have a little advice from him on how to study it. As I mentioned before, though many did not know, Lewis Carroll, the author of Alice in Wonderland, was a professor of math and logic named Charles Dodgson, and Lewis Carroll was his pen name. And in his book Symbolic Logic and the Game of Logic, he offered the following advice to his readers, which I now offer to you. The learner who wishes to try the question fairly, whether this little book does or does not supply the materials for a most interesting mental recreation, is earnestly advised to adopt the following rules. Begin at the beginning, and do not allow yourself to gratify a mere idle curiosity by dipping into the book here and there. This would very likely lead to you throwing it aside with the remark, "That is much too hard for me," and thus losing the chance of adding a very large item to your stock of mental delights. This rule of not dipping is very desirable with other kinds of books, such as novels, for example, where you may easily spoil much of the enjoyment you would rather get from the story by dipping into it further on, so that what the author meant to be a pleasant surprise comes to you as a matter of course. Some people I know make a practice of looking into Volume 3 first, just to see how the story ends. And perhaps it is as well just to know that all ends happily, that the much persecuted lovers do marry after all, that he is proved to be quite innocent of the murder, that the wicked cousin is completely foiled in his plot and gets the punishment he deserves, and that the rich uncle in India, question, why in India? Answer, because somehow uncles can never get rich anywhere else, dies at exactly the right moment, before taking the trouble to read Volume 1, page 12. This, I say, is just permissible with a novel where Volume 3 has a meaning, even for those who've not read the earlier part of the story. But with a scientific book, it is sheer insanity. You will find the later book hopelessly unintelligible if you read it before reaching it in regular course. Don't begin any fresh chapter or section until you are certain that you thoroughly understand the whole book up to that point, and that you have worked correctly most, if not all, of the examples which have been set. So long as you are conscious that all the land you have passed through is absolutely conquered, and that you are leaving no unresolved difficulties behind you, which will be sure to turn up later on, your triumphal progress will be easy and delightful. Otherwise, you will find your state of puzzlement get worse and worse as you proceed, till you give up the whole thing in utter disgust. When you come to any passage you don't understand, read it again. If you still don't understand it, read it again. If you fail even after 3 readings, very likely your brain is getting a little tired. In that case, put the book away and take to other occupations, and next day, when you come to it fresh, you will very likely find that it is quite easy. If possible, find some genial friend who will read the book along with you and will talk over the difficulties with you. Talking is a wonderful smoother over of difficulties. When I come upon anything, in logic or in any other hard subject that entirely puzzles me, I find it a capital plan to talk it over aloud, even when I am all alone. One can explain things so clearly to oneself. And then one is so patient with oneself. One never gets irritated at one's own stupidity. If, dear reader, you will faithfully observe these rules, and so give my little book a really fair trial, I promise you most confidently that you will find logic to be one of the most, if not the most, fascinating of mental recreations. Mental recreation is a thing that we all of us need for our mental health, and you may get much healthy enjoyment, no doubt, from games such as backgammon, chess, and the new games called massive multiplayer online games. Just kidding. All right. But after all, when you have made yourself a first-rate player at any of these games, you have nothing real to show for it as a result. You enjoyed the game and the victory, no doubt, at the time, but you have no result that you can treasure up and get real good out of. And all the while, you've been leaving unexplored a perfect mine of wealth. Once master the machinery of logic, and you have a mental occupation always at hand of absorbing interest, and one that will be of real use to you in any subject you may take. It will give you clearness of thought, the ability to see your way through a puzzle, the habit of arranging your ideas in an orderly and get-at-able form, and more valuable than all, the power to detect fallacies and to tear to pieces the flimsy illogical arguments which you will so continually encounter in books and newspapers and speeches and even in sermons, and which so easily delude those who have never taken the trouble to master this fascinating art of logic. Try it. That is all I ask of you. Lewis Carroll, 29 Bedford Street, Strand, February 21st, 1896. And thinking of Lewis Carroll puts me in mind of his more famous book, Alice in Wonderland and Through the Looking Glass, which is full of philosophy and logic puzzles. Perhaps you will remember what happened to Alice when she first got to Wonderland, when she fell into the pool of tears. At that point, Alice thought one of the first basic thoughts of philosophy, that the greatest mystery is not found in the world around us, but in thinking about this. Alice took up the fan and gloves, as the hall was very hot, she kept fanning herself all the time she went on talking. Dear, dear, how queer everything is today. And yesterday things went on just as usual. I wonder if it had been changed in the night. Let me think. Was I the same when I got up this morning? I almost think I can remember feeling a little different. But if I'm not the same, the next question is, who in the world am I? Ah, that's the great puzzle. Who in the world am I? That is indeed the great puzzle, maybe the only one that matters, the puzzle of self-knowledge. Here Alice echoes an earlier thinker, Socrates, who Plato reports as once saying this: I must first know myself, as the Delphian inscription says, for to be curious about things that don't really matter to me while I'm still ignorant of my own self would be ridiculous. I want to know about myself. Am I a monster, more complicated and swollen with passion than the monster Typhon, or a creature of a gentler and simpler sort, to whom nature has given a more divine and humbler destiny? Who am I? That's the great question. And what is the use of practicing the rules of thinking and learning to use all the rules of logic unless you use it to think about something important? In all our study of logic, remember what it is ultimately good for: to help you think about what it means to be awake, aware, and living as a human being. Ultimately, though logic can be a fun game, and there's nothing wrong with games, its ultimate purpose is to be a propedeutic for doing philosophy, which is always the love of wisdom, which I think Lewis Carroll understood quite well. There's nothing more serious than a game. You have to follow the rules, and the delight it gives you comes from following the rules, And games are a sort of practice for life, a way of meditating and becoming aware and opening ourselves up to the great mystery of who we are. So let's think about our first 8 rules and begin to play this game so that we can begin to get better at thinking and get to know ourselves a little better too along the way. Right? Now the rules we'll use are argument forms, which we're already familiar with. I've been trying to get you used to them all semester long, such as modus ponens, modus tollens, constructive dilemma, and so on. You should have these memorized already. And each form gives us a rule for making one step in a proof. Now note well, the rules can only be applied to a whole line of a proof and never to just part of it. The rules we learn after this, the rules of equivalence, are different, but we'll get to that in a little while. Now, we've also talked many times about the notion of a form of an argument and an instance of an argument, right? And so here we have the argument forms, modus ponens and modus tollens, which we're going to call Rule 1 and Rule 2, right? And as you'll recall, the variables represent sort of blank spaces in which formulae that maintains the same form can be substituted, right? P then Q, P therefore Q. P then Q, not Q, therefore not P. And no matter how large the formulae are, as long as the pattern is universally substituted, the rule applies, right? So if we had A and B, then C or D, and then we had A or B, we could get C or D by modus ponens. And similarly here, if we had if A and B, then C, then W, and we had a not W, right, we could get, look at that, I've got an error there. Let me fix that. I'll just let you see me being human here. All right, let's fix this thing. Y'all know your professor's human, right? Okay. So with my error fixed, we see we have P then Q, not Q, therefore not P. Another neat way to try to feel your way into looking for instances and seeing where the patterns are is to use colors, right? As long as you keep the colors the same and you make sure you don't make any mistakes like that. There we go. All right. P then Q, P therefore Q. So if you look at this instance, it has that form. P then Q. The point is the main operator. The main operator joins 2 units. Whatever is on this side, remember, is the antecedent. Whatever is on this side is the consequent. Basically what we're saying is, if anything, then something else. Anything, so something else. And here we have anything, this whole thing. As long as you keep the same patterns, you have that form. Here's another one, right? P then Q. P, therefore Q. And here we can play with modus tollens in the same way. P then Q, not Q, therefore not P. And if we have A or B, then C and D, that's the P, that's the Q. And if we then negate the Q, which is the C and D, we get the negation of the A and B. P then Q, not Q, therefore not P. Similarly here, antecedent, consequent, deny the consequent, we get the negation of the antecedent, right? P then Q, not Q, therefore not P. You have to get very good at spotting these patterns to do the proofs. So you want to let all this sink in. So consider an argument, for example, on an exam, because I'm sure we want to keep that in mind in our game of symbolic logic. I could give you an argument, so I'll tell you to translate it and do a proof. We may conclude that you should not trifle with the dragon, for if you are usually careful, then you won't get burned. And if you're usually careful, and you are usually careful, but if you trifle with a dragon, then you will get burned. So there's my dictionary, right? That's the conclusion. You shouldn't trifle with a dragon. So that gives us U then not B, U, T then B, and not T. So consider the patterns, right? P then Q, P, right? That's what I notice right away. I've got a modus ponens pattern there. P then Q, P therefore Q. So if I have P then Q and P, I can get Q, right? And so there I go, line 4, I say, this, right? These are the premises, 1, 2, 3. The slash means the premises are over, and that's the conclusion. And now I begin my proof. And I've got not B, and I get it from lines 1 and 2 by the rule of modus ponens, right? Now all of this and the colors I'm just putting in to help you think about it, okay? You don't do the colors. Well, you could if you want to, but probably not. All right. Then if we continue our proof, because we're trying to see if we can find not T, that's the game, right? Given this, to see if we can get to that. I've got the not B from 1 and 2 by modus ponens. Now I notice I can get a not T from line 3 and 4. P then Q, not Q, not P. Right? P then Q, not Q, therefore not P. And that gives me a not T, and I've completed it, right? I've been given that. I want to see if I can get to that, and I've got to that. And so the proof is over. And I could write QED, or I could put the funny little black square called the tolman there if I wanted. But it's enough for me if you just reach the end of the proof, and there we have it. Okay. Now let's think about 2 more rules and how we look for patterns, right? You'll remember disjunctive syllogism, right? P or Q, not P, therefore Q. And it has a second form, P or Q, not Q, therefore P. You've done truth tables for this, and so you know it's valid, right? So you know it's a rule we can use. And in essence, what it's saying is if you got anything disjoined, right? That's what we mean. This is a disjunction, right? If you have anything disjoined, right, P or Q, and you negate one side of the disjunction, you can get the other side. If you've got a disjunction, 2 parts joined by the V, and you negate one side, you can get the other side. So here's something joined by the V, right? So if we negate that side of the disjunction, we can get that side. And similarly here, we have P or Q. This whole thing's, just imagine a box drawn around it if you like. And if we negate that side of the V, then we can get an A. You also know that the rule of hypothetical syllogism is valid because you've proved it with a truth table. P then Q, Q then R, P then R, right? And basically if you got if you've got an antecedent and a consequent, and then that consequent becomes the antecedent of something else that is a consequent, then you can go from this antecedent to that consequent, right? So here we have P then Q, Q then R, so we can get P then R. So think about this argument with me. Either I drink 6 beers or I study logic. If I ignore the need to study, then I want to take this logic class again because I need the M, right? The M requirement. And I will drink 6 beers only if I ignore the need to study. But I do not want to take logic again. As much as I've enjoyed it, I do not want to take logic again. So I study logic. So there's my dictionary, and I translate it, right? I list my premises, D or S. If I then W, D then I, not W, therefore S. And the point is to see, using these 4 premises, can I get to the S? Well, look, D then W from 3 and 2, right? D then I, and I then W. D then I, and I, it doesn't matter what order they're in the premises, right? In your head, you rearrange them. D then I then W gives me D then W. Right? Now, if I have D then W, I notice D then W and a not W. That makes me think of modus tollens. I can go D then W, not D. Right? And now that I have this not D, I look up here because I've been looking for an S, and I think of disjunctive syllogism. I've got D or S and not D. That'll give me S by 1 in 6 disjunctive syllogism. And I'm done. QED. It's been demonstrated. Now, remember, an inference rule has to be applied to an entire line of a proof. Otherwise, it won't work. So here, I just have a simple instance of modus ponens. If A, then B, A, therefore B. And that's correct. But over here, I have if A, then B, and C, and I've tried to apply it just to that part to get the B, but that won't work. Think if the rules only apply to a whole line, then this whole expression is a conjunction. Remember the idea of the main operator, right? The main operator here is the and. So I can't use an arrow rule, right, on an and. I could, if I wanted, break off the C, as we'll learn in a little bit, but that's for the next class or the next video. So I'll be recording another video for you shortly. I decided to break these up into little smaller chunks so that we don't get all mind-boggled trying to take it all in at once. So I'll see you soon. Thank you for your kind attention.